on say A, not who I'm gonna be.
Okay, we can get started. Homework's due tonight, and there's office hours today. I want to remind everybody that team registration is due Wednesday, and only one team is registered so far. Only one good team. I don't know about the rest of them. Then the other homeworks have already been released for the rest of the semester. This is all that you have due as far as homework for the rest of the semester. After you guys register for your teams, actually on Wednesday, we will release the project meeting schedule. And you guys can go sign up. Your team will sign up for a slot. You'll come to my office or Matt's office or James' office for 30 minutes, bring some basic slides, and we'll review your project and give you feedback. Yeah?
I forgot, was there a homework drop in this class?
There's no homework drop in this class. Yeah?
During fall break?
Nope.
It's 13th.
It should be, that date's wrong. It should be like the 20th or something. Let's go look. Let's find out together.
Oh, Monday the 20th. Yeah, that would make sense.
So yeah, next week is fall study breaks. You don't technically have a lab due. Right? You can work on your lab if you want. Your project proposals are due Wednesday. So I mean it's a little unfortunate. Actually, I just need it 24 hour, or I need it the night before your meeting, so you could do it on, if your meeting's on Friday, you could do it Thursday night. Again, you're going to bring slides. Yeah, so there's going to be no formal class next week on Wednesday. We're going to use that time for project reviews.
I heard someone.
Any logistics questions?
Yeah.
This is 20th. This is 27th. Anything else?
Let's see. Was it 270?
No, this was the last one.
If you guys are having trouble finding teammates, come see me after class. We can spend a little bit of office hours doing some matchmaking, trying to get everybody into a team. All right. So we're going to move on to SPI. So it's a serial peripheral interface. This is another one of the communication buses. Readings here. So again, you guys should be at the point where you can read the manual. There's also, this textbook gives a fairly good review. But serial, SPI, UR, I2C have been around for a long enough time that you can find good tutorials online as well if you want a different take. I would look at the major vendors like Analog Devices, STM has tutorials. Any vendor that makes chips typically has a tutorial for these things anyway. So you can guys look around and find other tutorials for this topic. But I'll give you the basics here. All right, so SPI stands for Serial Peripheral Interface. One of the most common communication protocols has 4 wires plus ground. You always have to remember that there is ground. If you don't connect ground between your devices, you will not get any data transfer through, or you get very poor data transfer. It's typically used for chip to chip. This is not USB where it's devices to device. You have a single controller and multiple peripherals. It's fully duplex, meaning that it's transmit and receive. Can you guys hold on for a second? Thanks. So the controller can transmit and the peripheral can transmit at the same time. Typically, it doesn't happen that way, but as possible. And it's nice that it gets up to multi-megabits per cycle. One of the challenges with SPI is it's not official standard. Like, it's a de facto standard in that many chips and manufacturers follow it, but it's not like it's an IEEE standard where they regulated every last little bit of this. So that means that there's a lot of freedom in here. It's a very basic protocol, but it also means that not every vendor is gonna follow the same rules. And we'll see some of the caveats as we go through here about how the standard has evolved over time. So here's an example of wiring. So here we have a controller and 3 peripherals. They each share bus lines. So here we have SDO, so see, controller out, controller in, and then you have a common clock that goes to all of them. And then to do the arbitration, that's where you're telling, the controller tells which one I want to talk to. There's a little chip select, so you have to have N extra on the controller, N extra lines for each one of your peripherals. So this is a lot like how advanced peripheral bus had its controller and its peripheral would go through and select which ones it was going to interact with. And remember, there's different registers inside of your advanced peripheral bus peripherals. There's also different registers inside of here. So you'll get a data sheet and they'll say, oh, there's N registers in here, and this is the way. They'll tell you how to index them and how to send data in and out of those registers. So serial data in, serial data out. System clock, maybe we shouldn't say system clock, it's just the clock of the controller is using for that. And end select lines. The controller selects the peripherals by pulling it low. Controller generates a clock, and it shifts data out on the clock edges. Any questions? Okay. This is called synchronous or fully, it's a synchronous protocol in the sense that the clock and the data are aligned, so there is a clock. It's fully duplexed in the sense that the idea of how this was originally developed is that there's a register here and a register here, and that on each clock cycle, data is being transmitted out, is being shifted out. So basically, let's see, how would we do this here? Like this is shifted through that way. And so here you can start seeing that typically, like if your controller is sending out data here, your peripheral isn't necessarily going to send out whatever is here. It could, that's how it's designed, if it had a message to be sent out. But if it has nothing, it'll just send out all zeros or all ones, whatever its default status is. But the idea here is these two shift registers that have been put together, they're pushing data back and forth to each other. Packet sizes, it's usually 4 to 16 bits. 8-bit is typical. 8 bits is just what ASCII characters are. It makes it life easier. That's usually the packet size to go between the two. There's no acknowledgments. There's no flow control bit. So there's no parity bit like we saw in UART. There's no start or stop bit. It is just send out clock edges. You're not always sending out clock edges. You only send out clock edges when you want to communicate. You're going to use chip select to select the peripheral, and then that's when data is being put out on the line. Yeah?
So all this does is swap data between the two things.
Yeah.
So how do you like write something new to one of the, so let's say the controller wants to send new data. Like all I see is like, the only way the controller can change it is if it reads in from the peripheral.
I mean, this is the base format of how it works, right? So now you could have combinational logic over here that looks at this register and says, I've gotten a full new 8 bits. I'm supposed to do something with it, like get my accelerometer data and send that back. But this is just the underlying mechanism of how data is transferred back and forth. And so the SPI peripheral can choose not to send any data back when data is coming through if it has no data ready to send. So if it was all zeros, it wouldn't send anything.
How do we know when all the bits are swapped? Is that in the packet itself or on the outside?
How do you know when all the bits are swapped? So you have to agree beforehand. You're going to look at the data sheet and say this peripheral or this device requires 8 bits or 16 bits or 12 bits, whatever it is.
Yeah.
And then, so you have to know a priori how that works, and then you're going to shift out that many bits. So it's not required there's only an 8-bit register. This is typically how you would think about it, I suppose. It could be larger, 14 bits.
Yeah, that's why I'm saying, like, is there a counter or is it handled within this?
You would configure your serial peripheral device to be this many bits.
It's just for transaction.
Yeah.
Okay.
Yep. And you do multiple transactions over and over and over again. So say you're trying to read all 3 axes of an accelerometer, you'd say, give me the X. And then it would prepare a packet, then you send out clock edges to get the 8 bits for that. And then you send out another one that says, give me Y. And then it would get that thing, get it ready, and you send out more 8 clock edges to receive it. So you can only transmit data back when it's receiving clock edges. Yep.
So who's generating the clock?
The controller.
And it's sending the clock to
All the peripherals. So here, it sends it to everything, right? It's just the trick is only chip select for that peripheral is going to be enabled. Just like the peripherals on the APB. What do you think about that? Believe it? Believe it? Okay. Could say, I don't believe that. That's horrible. Okay. Yeah.
So they're like SPI control, like for I guess for the STM, like does the SPI controller have like a finite amount of allowed peripherals since there needs to be an enable pin for each one?
You typically will reassign one of the GPIO pins to act in that role, and you have to tell your peripheral, hey, this is the pin that controls that. It can be somewhat painful if it's like the STM. I'm trying to remember the STM. STM does like have some predefined pins, but if you wanted N, like more than that, then you have to kind of like push it into the protocol, or sorry, into your code. What other questions do you have? So I just want to go through this block diagram. I mean, really, the thing to take away from all of these serial protocols is really a shift register. Why do we use shift registers as the core? Because that's the interface between the massively parallelized world, right? 32 bits is your core versus you've got this limitation. So this is the controller. This would be your GPIO pins. You have this limitation. You can't get 32 pins out. You only got 4 pins. A limited number of pins, and so now you have to shift everything from the parallel world to the serial world, and then you clock it in, then you get the serial world back to the parallel world. So it's really this whole protocol, all the protocols of serial are based around this constraint of GPIO pins. And so in this little thing, I'm trying to remember how it works here, we have some data up here, we have load, we have a clock that's going through, let's see, where's the clock, not clocking? No, this is on a sequencer, so it just does 8 clock cycles every so often, not continuously, which makes sense. And then let's say I'll select a device, I'll select that device, and then I can go and shift out data. That's gonna work. Oh, no, I have to go this way. Now it got a little bit off cycle, but now you can see that I'm shifting data out from here into there. And then you would just go, because I screwed it up, go and select the other device and shift out data to the other side. And then as we get to the end of those 8 clocks cycles, stop here. You know, you're going to have some logic internally that says, okay, 8 went past, or whatever the number is in your data sheet, 8 went past, and now it's time for me to do something with this data, right? To take that data, the peripheral will do some action with that data. Typically, it's getting prepared to send data back. Usually it's a request, you're send me some data, and you get some data back. Yeah?
I'm confused since the part where you say, oh, I screwed it up, I'm going to select the other device. Is it like...
Sorry, say that all again.
So, I'm a little lost after you said I screwed it up. I'm gonna go to select the other device. So I'm not really sure why we have to have 2 devices, or is this like an example?
It's just an example. You only need to have 1 device. I just started clocking data out in the middle. I didn't load the data out of the controller shift register until halfway through 8 clock cycles. I didn't align that, so your microcontroller better be better at that than me. And then I just redid the experiment by going to the other shift register, or the other peripheral.
And usually it will be the programmer's responsibility to make sure that we enable it in the right timing, or?
Yeah, I mean, you as a programmer are going to do that in conjunction with your SPI peripheral. So you have a whole peripheral on your device, and typically what it's going to be is you're going to send data in, and you're going to tell it to go, and then it will take care of the rest. And you're going to have to set it up and tell it what's the clock priority, the number of bits you're going to send out, all that sort of stuff. You just load a register and then say go. That should be essentially what it is. Any other questions? Great. One of the, nope, what is this, SPI? I2C. That's not the right lecture. One of the challenges is the timing of when you clock data in and how it's clocked in, because there's no formal spec. Or IEEE, everybody agreed on spec. So it's kind of evolved over time. The most basic case is here you have your clock. This is your control line. Remember, your control line or chip select goes low to select the chip. It helps the peripheral know that there's anything connected, right? So if the pin isn't ever high, then the peripheral says, well, I'm not even connected to a bus, right? There's a little timeout in it. But here, when it transitions from high to low, you go and the chip says, okay, I'm about to be talked to. Then you have serial data out and serial data in. So this is from the out of the controller's point of view. So it's out, and then serial data in from the controller's point of view. And so here's the bits that are possible to be clocked in. And so a normal clocking regimen here would be, you're going to go and on, say, the rising edge, you're going to clock in the data because the data is stable here. You don't want to clock on the negative edge in this particular case because the data is in transition. So you're going to clock right in the middle of that eye diagram. So these are typically called eye diagrams because of all the data that is going high, this is the highest part, this is the lowest part, and then you want to shrink the time to the point where it's as small as possible such that you can transmit data through reliably. If it's too small, then you'll get corruption. That's just the convention of how these diagrams are made. But this is not the only way that they can clock data in and out. So they have a somewhat complicated at first set of options. There's up to 4 different modes. And so here we have clock polarity. This row here is clock polarity 1, this is clock polarity 0. And basically what you're saying is the clock normally low or is the clock normally high? So there's 2 different modalities. Here is rising, here's rising, here it starts low, starts high, goes low, and back. So that's the 2 different clock polarities. And then you have the phase. What they're saying is where is data latched in and out? So you can either latch, here it's sampling edge, here's the toggle edge. So here, toggle edge being when the data is toggled. Sampling edge is on the first edge, and here sampling edge is on the bottom. So now you can imagine you have 4 different ways in which data can be clocked in and out. And so you have to know what your peripheral does. All right, if you're doing something different than your peripheral, it won't work. And it used to be that not all microcontrollers would support these. So I certainly had back in the, I don't know, I guess late 2000s, I had bought a chip, I think it was mode 3 actually, that was not compatible with my microcontroller for whatever reason. It was insane. I'm like, well, how could this possibly be? So I had to go and put like a little inverter just to invert the clock line to make it all work. Made me insane. How do we feel about all the different clock edges? Can't tell. Yeah, one brave person.
Sampling versus toggling.
So sampling is when the data is sampled. Toggle is when it's changing between states. So here, this is when data is sampled. Here's when data is toggling between the states. So then, the reality is you get some horrible complicated timing diagram like this, which is trying to show you all the possible phases for one set of bits. And so here we can say this is your clock, this is your polarity of your clock, and this is your phase of the clocking. So here we're positive, and we're clocking on the first edge, so this would be this one, 0, 0. We can go down here, and they just show that the data happens up all at the same time, which is a little bit confusing, but they're just advancing or slowing down the start of the clock just to make it all align in this diagram. And here you see the polarity is inverted, and the phase is on the falling edge, or on the second edge, so over here. And so here you can see that here had a negative edge. It started out positive, went down to negative. So that would be inverted polarity. And then on the second part of that clock edge is when data is sampled in. So you just have to keep track what your device expects and be able to walk yourself through this diagram so that you know what you're expected to do.
So I'm looking at like the top and bottom one and then the 2 middle.
Yeah.
Those ones look almost identical to me, except for like the very beginning and the very end. Could you explain why there aren't just 2?
It's polarity, clock polarity. This starts high, this started low.
Oh.
Yeah, it's subtle. But you can also just see, it's also in the nomenclature here. But yeah, they are very similar. You can get lost. Yeah?
Why are there 4 different modes for this?
Because they have 2 free parameters, so you can either be positive or negative polarity or positive or negative phase. So then that's just the logical combination of the 2. Does that answer the question?
I don't get how it would benefit.
Oh, why in the world would people do this?
Yeah.
Oh, that's a whole nother story. The problem is that there's no standard. So some manufacturers did it one way, some manufacturers did another way, and now we're stuck with all of this. Thankfully, your microcontroller supports all of them. But yes, there is no, you could just choose one of these and it would have been fine, but that's not how we inherited this world. Yeah.
So as far as the modes, you're thinking about polarity of determining falling edge.
Polarity, think about clock polarity is what is the resting state of the clock? When there's no clock signal going on, is it low or is it high? That's what polarity is making you think about.
If the clock is high or low.
Correct.
The phases, are we looking at the first or the second?
Yep. Yep. All right. So data, let's see, what am I trying to tell you here? I don't want the slide, I want the slide. So here's an example of a typical transaction. So here, you're in idle, the controller's in idle, the controller is sending out clock edges. Here it happens to be, I think we could figure out what mode this is, maybe this is mode 3. It's saying that you're gonna clock data in here, and then it sent out some data as well. So these two are generated at the same time by the controller in this case. Now, you might say, why is there nothing being transmitted back? I thought this was that shift register thing. Well, the peripheral has nothing to say. Yes, that data is being shifted out technically, but the peripheral has nothing to shift out. So it's just gonna keep it all ones. And then you can go line up, here's what the data is that's being sent out. So it said ASCII S. And then the typical case is that this is some command. Again, you're going to read through the data sheet for your SPI peripheral. This is some command, and then the peripheral has to respond. And you have to know what this timeout value in between is, right? So it can't respond immediately. There's some point where this would be too short for the logic in here to respond. So there's typically some timeout thing you'd have to read through your spec. Typically, it's not big of a problem because your microcontroller just has some built-in timeouts already in it. So anyways, you're gonna go out here, and then you're gonna send out another 8 clock edges, and this is the opportunity for the peripheral to send data back. So the peripheral is pushing this out on serial data in from the controller's perspective, and now it's sending ASCII F back to the device. Yep.
In the bottom right corner, it has a little dash on the chip select.
Yep.
Is that supposed to be this after last byte center receive?
So you could keep this going if you wanted to keep a transaction.
Yes.
Just keep this thing active. Or you could go back up to high if you're done having a transaction. This is a way to kind of tell the peripheral, hey, you're expected to respond, but if this goes high, and say you send an S, and S is a magical command that says, I want to receive data, and then you went high, it's not going to send you anything back because you haven't ship selected it, even if you send edges out. All right, that's a typical packet structure. SPI does not have a standard or a maximum data rate associated with it. It uses push-pull CMOS, so it can actually go very quickly. It just depends on the drive strength of those output CMOS devices. So when you're looking through your data sheet, you have to make sure that you're matched in terms of speed. Sometimes you can go much faster than some devices can go much faster, and you just have to look at, what is the spec for your particular device. You need to read the data sheet for everything. Some standard specs, standards in quote, but you can get up here to, hundreds of kilobits to megabytes. There are some systems that go up to hundreds of megabytes. Cameras use a version of SPI called CSPI, I think, and those go particularly fast. Yeah.
On the previous slide, when they're doing the swapping, does the controller send the data and then the peripheral sends it back, or is it happening at the same time? Like, is the swap like when it's getting input, is it also giving output at the same time?
Yes. So it pushed out a 1, it got a 1 back. It pushed out a 1, it got a 1 back. It pushed out a 0, got a 1 back. It just had no information to send. So this idea of 2 shift registers, they're shifting data back and forth. That's like the foundational material of how these things were originally set up. It's a good way to think about them. Now, it just may be that it's not actually how your device manufacturer implemented it because there is no spec. There's no, but this does allow for, you could, in some devices, you can send out commands and receive data from the last command at the same time. So you can do fully duplex, sending data back and forth, so you can increase your overall data rate. Okay. So one challenge with these devices is that there's no inherent way for the SPI peripheral to tell the controller, I want to talk. It's not part of the protocol. Just like with the ABI or APB peripherals, there was no inherent way. And that's a challenge for some devices. So you take like a gyro or an accelerometer, when laptops first came out, they had spinning disks and it wasn't all solid state. And what they do is put a microcontroller, or a MEMS accelerometer in there, and when the MEMS accelerometer measured free fall, right, it's no longer accelerating, no longer feels the acceleration of Earth's gravity as measured by that cantilevered capacitor, then it would say, oh no, watch out, I need to pull the head off the disk so that when it hit the ground, the disk wouldn't ding the platter and destroy some bits. So oftentimes you need some way for your peripherals to actually cause some action over here. And so the way you have to do that is you kind of go out of spec. Well, there's no real spec anyways. So they say you'll oftentimes have interrupt pins. So these interrupt pins will not be part of, say, your SPI peripheral. STM doesn't know that they exist, so that's not an option, but you'd have some GPIO pin, you set it as an input interrupt, you'd say rising edge or falling edge, and then that will cause some interrupt on your device to go off, under which condition you can go say, read out the data and tell me what happened. And then you can take the action to pull off the head off the platter. Does everybody know what I'm talking about with hard drives? Does everybody know how hard drives are made? Old disk ones? I get some shaking heads. Back in my day, they used to have metal disks with memory magnets on them that would spin. All right, it's probably good just to know, learn, watch the 2-minute YouTube tutorial on how magnetic disks work. They still use them today. It's important stuff to kind of have in the back of your mind. So we talked a little bit about shifting stuff in and out. There's some extra features. There's different ways that this can be used, and people have changed the protocol over, or reused the protocol in different ways. So say, we could go back up to this example as a motivating example. So here, the challenge here, I have to have what? 4, 5, 6 wires to talk to all these things. Maybe you were wire limited. So people will do things like have the serial data out from the microcontroller's perspective, send data into peripheral 1, and then the out of peripheral 1 goes to peripheral 2, and so on and so forth. And so now I only need to use 4 to talk to N chips. Now the challenge is that these chips have to be set up for this condition in the sense that you don't want each one of them reacting to the command, but you could shift a command all the way through, and then you could shift a command all the way through. So this is how LED strips that you can individually control each LED typically works. You have some color code, so say this is green, this could be any color, so you say you want this one green, blue, and red, and what you do is you shift that red all the way through. You do it so fast that humans can't see the small color change that occurs when red was here, and then red moved, then red went here, then red, and then when it stops, then you will see the correct colors. So that's a way in which to not have to have a chip select for every single LED on your thing, but you can go through and just push the data through. You just have to do it faster than humans can detect. Does that make sense? Yeah.
Why does it have to be serial?
You could do parallel. But then you have a wire problem, right? So memory, for instance, you want to do parallel. So you might have a 32-bit bus to talk to memory, but that's a high data rate scenario, and you want it to be very quick. So designers are willing to pay the penalty of all that wiring nonsense just to get that performance. But here we're going to be in the world of serial where you're saying like, we really care about pinout, we care about layout size, we're slow. We're like, our microcontroller is going at 120 megahertz. It's not gigahertz. So since we're so slow, we're just going to assume we're in the world where we're willing to pay the penalty for slower data rates for the convenience of having less pins. It's a good question. Any other questions? Yeah.
Peripherals need any extra hardware support to do daisy chaining, or can they do it with the standard hardware that they already have?
Typically, they can do it in the standard hardware configuration, but your peripheral has to be kind of set up for it. And so there are peripherals that can be daisy chained, but some of them I've never expected that because there's no spec. So imagine you've written an S into one, and you really want the next one to react to it, but the first one starts reacting. That would be a challenge. Yeah, what is this telling us? Just that in this particular case, the word for U2, which was here, starts off here, then transfers to U1, and then U1 transfers it to U2. All right, so you're on your STM32, you have 3 SPI modules. Each module has its own IRQ lines. Now you have a really beefy, like 128-pin device on your dev kits. Typically, you don't have that many if it's much smaller. Yeah.
Question for the previous slide.
Yep.
So if a lot of the designer constraints are surface area and then the clock speed or clock frequency, why is there like no really big handshaking parallel?
Why is there no big handshaking?
It's like I feel like a lot of these handshaking protocols are mostly serial.
I mean, they definitely exist for parallel. It's just in the world of microcontrollers and embedded systems, you typically don't have large parallel buses. So we saw for the APB bus, that's a parallel bus. That's a 32-bit address, 32-bit data. They did have more handshaking things, right? You had like your P-ready, your P-enable, P-select, all those lines. But here, because we're I/O limited, we're just not in that type of world. So typically, there's this conceptual difference when you go from microcontrollers, which is bare metal programming, C, free RTOS sort of world, then you go up to an application class processor. So we're in the Cortex-M, Cortex-R environment. You go up to Cortex-A, so the application class, then you're in embedded Linux, and now it's much closer to a low-end desktop processor. And then you start having things like parallel buses to go talk to memory, external memory. It's just, we're not in that world yet. That world also costs a lot of money, you know, if you want to dev in it, so. Okay. So you have this big, ginormous chip, but you also have multiple SPI modules, each with their own external interrupts. You have DMA support, which allows you to, without the core's control, without the core doing any tasks, data can be transferred from your SPI bus to memory. So you can imagine if you had some peripheral that was just going to be streaming you lots of data, you didn't have to react on any one data byte. Maybe you looked at 64 data measurements, and then you want to take the average or something. You could just have DMA push that directly into memory, and then when your core gets the interrupt, it takes that data out of memory and does some tasks with it. Hardware CRC features. Really? I didn't know it had. I don't remember that. CRC controller. It must be It must be for very specific devices. I don't remember any peripherals in the lab that actually use CRC. Suppose there are some, and your device has support for it. Again, that's really dependent on if your peripheral uses that or not. So the pros and cons. So straightforward wiring, 4 wires, 3 plus N for the, N being the number of peripherals that you have, because that's the chip select line. You also have to have ground. It's much faster than the asynchronous. It's faster than UART, and there's no addressing, right? From the arbitration point of view, it is simple. You just tell which one you want. There's only one topology. It's going to be a star topology. I guess you can do the daisy chain and those sorts of ones, but they are more rare. Chip select, the cons are chip select does not scale with a large number of peripherals. So if you have many, so say 10, that's a lot of GPIO pins to dedicate to that. You might want to switch to a different protocol like I2C, which is address-based. We'll talk about that later. There's no acknowledgement bit. There's no flow control whatsoever. So if the peripheral misses something, then it's the controller's job to kind of try to figure out what happened. Why did the data get garbled? You don't really know what happens. And then the controller has to initiate all communication. Yeah.
This might be a stupid question, but for the peripheral's not like scaling with the number of lines or whatever, is it feasible to have like one main controller and then have a bunch of sub-controllers going into
Oh yeah. And you find there's lots of workarounds for these sorts of things. So, this is a pretty easy, doable configuration. But sometimes what you have is you'll run out of pins over here, or you're just a lot of devices. You might have what they call a bridge, which will be an SPI bridge that will go from SPI, and then you will send commands into here, which will break out into more SPI lines so that you have more chip select pins. A more common one is something like an I2C extender or a bridge where you talk I2C, and then you want to talk, we'll talk about this in a minute, you have devices with conflicting addresses, so then you have another device in between that changes the address. So you talk to one address that's different from here and talk to the other one. So there's all these extra helper chips to get around the limitations of these protocols. Typically when I see these problems, you have to be like, do I really need to solve it this way? Because it's usually like a lot of headache, but there are helper chips. Other questions about SPI? All right, we're gonna move on to I2C then, which is the last major peripheral that we talk about in this class. The intra-integrated circuit. Nobody has ever called it that. Every year I forget what it's called. This is called I2C or I2C. Usually this 2 is raised up a little bit, but not all the time. But that's where the I2C comes from. So there's some reading if you're interested. So what is I2C? So this was a standard that was invented by Philips in the early 2000s because they wanted to be able to have a different serial communication protocol to talk to all the chips on the television. And now this is the de facto 2-wired communication standard. If you only want to use 2 wires, okay, plus ground, this is the standard that you need. Now it's very common to have peripherals and used it for embedded devices. Like all the major manufacturers support it. It's just the trick is that each time that they want to, oh no, it's since 2000, no licensing fee. Oh wait, that's not true. So every time that this Texas Instruments or STM wants to make a peripheral that has a certain address associated with it, you'll see. And that address has to be registered in at least a database so there's no overlapping addresses. You don't want to have 2 devices on chip with the same addresses no one to talk to. So after 2006, they got away from the licensing requirement for, I think, the microcontrollers. However, there's still a fee. Oh, so the licensing for the IP, the intellectual property of the design, they got rid of. But you still need to acquire an IC peripheral. I guess it's now an XP, which actually costs something. So if you want to make a new I2C peripheral device, then you're going to have to register it and make sure it doesn't conflict. So this is the general topology here. You have a controller, you have device 1, device 2. There's only 2 lines, serial data line and serial clock line. And now it has these extra resistors up here. Okay. So each device has a unique 7, 10, or 16-bit address associated with it. 0 is for broadcast. It's not used that often. It has external interrupts or external pull-ups, and those are to return the line to high. So these things are open drain, which means they pull the line down, but they're not push-pull, so you cannot push the line high. It's only returned by those resistors, which means that the size of those resistors actually determine the speed of the bus. Does anybody know why a resistor would determine the speed of a communication bus? Yeah.
Isn't it like how quickly it can return to the like max voltage basically?
Yes, it is. And what's the defining factor?
Each pin has a capacitance, so the resistance in the capacitance forms the time constant that determines the rise time for the signal.
Yep, exactly. I'll just repeat that. So, and we'll actually see a little example of this. But here, there's a bunch of little capacitors. They call them parasitic capacitors. Parasitic in the sense that nobody designed them. Nobody wanted those capacitors there, but they exist. And so each GPL line has a little capacitor effectively to ground. It's generally the gates of your transistor, CMOS transistor, make a capacitor to the ground, plus your pins and everything. And so that limits how fast it can charge back up because you have to charge this capacitor. And these things are the thing pulling it up. So now you're in the race with RC discharge, RC charge, about how fast your device can go, which seems like a horrible design, but they were actually smart enough. There is a reason for it. But now you're in the mode where you have to choose the correct resistor size to go certain speeds, which is a wild idea. So inside, here are your open drain devices. So this is just a transistor gate. You may not be familiar. Here they put a diode here. So every NMOS and PMOS, there's an inherent diode built into it. And these are also probably beefed up a little bit because they're supposed to be over voltage and under voltage protection from static discharge. But they're here. And now you have a device where, say, here's your clock generator. It's going to send out square waves here. And then it's going to pull this node down, and then it's going to let go, and this resistor is going to pull it back up, and that will be determined by your peripheral. And then both of these, the peripheral and controller, both use the data line to send data back and forth. They just have to control and think about and coordinate about which one's going to talk when, because they're both reusing this data line to talk. Any questions so far? Yeah.
Why do we have to worry about the resistor thing for like SPI?
Why? Why don't we?
Yeah.
Because that's push-pull. So that's a fully it's NMOS, PMOS pair, so they can drive it high and drive it low. But they also have different data lines here. So they have a data line for transmit, data line for receive, so SDI, SDO. Here you don't have that, so you don't want to get in a case where one's driving high and one's driving low. That would cause an error. So this is the way to arbitrate across that from a hardware point of view.
Why do we have resistors in the first place? Like, couldn't we just tie the line directly to VDD?
But then if it's directly to VDD, then you cannot pull the line down because you can't.
Then it's short if you
It would short out. You'd have to pull, from a circuit diagram, infinite current, enough current that would brown out your system. So here's just an example how multiple devices would go. Got exactly why the slide's here, but it's a great slide, promise. So here, I really want you to think about there's multiple devices, and they only are going to they only have these two wires connected up, which is nice. The wiring is easy. These resistors can technically be anywhere on this line. It doesn't really matter where they are. If it was very long, you might have to think about something, but these resistors just have to be somewhere. In fact, if you remember on your microcontroller, they had internal resistors. Remember your GPIO peripheral had this option for resistors? Well, that's for this reason. STM is saying, hey, I'll put resistors in our device so that you buy our device instead of our competitors, and it will save you 2 resistors on your PCB. Is that a good deal? How much does a resistor cost? What? How much? 10 cents? Anybody lower or higher? Who's higher than 10 cents? Lower than 10 cents? All right, come on, give me another number.
0.1 cent.
Lower or higher than 0.1 cents in volume?
in volume.
Lower? How about another number lower?
0.01 cents.
0.01 cent? That's good. It could even be less than that. It could even be, a hundredth of a cent. Just because you just make so many of them. There's a machine that makes so many of them, and you buy it. You have to buy like 3,000 or 100,000 at a time, but you can get those prices very low. So it's not really a cost factor they're saving. STM isn't saving you a lot of money. Manufacturers don't really care about their cost of true resistors that much. However, it's space on the board. That's what they're saving. They're saving you space. All right, let's see if I have this one set up. Kind of look through how this peripheral will work. All right, let me reset it. All right, so here we have an I2C controller and a target. I have parasitic capacitance. It's off right now. It's not connected. And then we're just simulating here. We have a clock that is driving it into an NMOS transistor, and this thing is just going up and down, up and down, up and down, right? And this thing is pulling it back up. You can actually kind of see, maybe if I advance the current a little bit. You guys can see it pulls current down here, right? When that data goes through. And then up here, there's a register here, and you imagine this is a register, and we're going to put a bit out here, and it'll get detected by these gates right here. And this is just to convert the analog signal into digital, and we'll show you the output. And then we can send data back the other way. So for example here, I can go and send a low out here. And so that low went all the way through and is registered as, I put a high out here, and it's registered as a high over there. And if I go back the other way, I can send out a high. And, oh wait, it's gotta be a high. I can send out a low. I gave away the problem with this thing already. All right, so one of the challenges here is somewhere in here, I forgot where I did it, I sent data from this device to that device. In here, it sent device from here to here. So if you're looking on your network analyzer, or your oscilloscope, and you see this data trace, and you're like, well, why doesn't my thing work? It's hard to even know which device was talking. Boy, it's a pain in the butt to try and debug these things. The other problem that I fell victim to myself is that the natural state here is that the line is high. So the controller can go through and send data. Great. The receiver can send data, or the peripheral can send data. But if the receiver is pulling the line low, and some other device gets on the line, see, I'm toggling this pin, and the line's not going up, right? Because this peripheral has, done an illegal thing, is just pulling the line low. So now this thing is hogging the line. I can't send any data back and forth. That's another error condition of this bus structure. Now, the benefit we get is only 2 wires for N devices. Nobody's raising their hand and saying this is horrible or I'm confused, so now I'm concerned.
So since there can be issues of sending at the same time, you have to add like additional hardware or software to prevent?
Software, there's an arbitration scheme where the controller needs to look at the line first, make sure it's high, pull it low, check to see if it was actually able to pull it low, and then it assumes it has control over the bus. But if it tries to pull it low and it doesn't go low, or I think actually they pull it low and try to raise it back high, on the first bit it tries to raise high, it's making sure that it actually goes high. And somebody else could have controlled the bus. Yeah.
What's the bottom part doing, and why is it not connected to the top?
What's this?
Yeah.
This is the clock. This is the clock line. We're seeing it's wiggling over here.
Oh, I see. It's giving it to the target.
Yep. The target can't generate a clock. Only the controller can generate a clock. And then the controller or the peripheral, whichever I decide, by clicking these buttons, is sending data back. What do you think about that? I sense
So depending on who clicks on what button to send
yeah.
to?
That's the problem, isn't it? It sounds horrible.
Well, what if both want to, so who decides that?
So it should be the controller. This decides who's talking when, right? So the controller is going to send out an address request. It's going to send an address over here. And then this thing says, oh, okay, you want me to respond? Then it will send out clock signals for it to send data back. But it could be that there's multiple, in this particular protocol, you can have multiple controllers. And now the multiple controllers have to fight it out through this arbitration scheme about seeing if the bus is empty or being used or not, to figure out which controller can use the bus. But usually if it's just one controller and N peripherals, the controller is going to say, hey, I want you to talk, and then it's going to send out edges that only that thing should be talking back.
What if the controller and the target would want to talk to each other at the same time?
Then it will not work. It doesn't, the thing doesn't blow up, right? So if I pull this thing low, so I'm low, and now all of a sudden the target wants to talk, it just can't do it. It's just not effective. right? I'm toggling it, but it cannot pull this line high. There's no way for the target to force that line to go high. Do you agree with that?
Yes.
Okay, so now we're just in an error condition, but nothing blew up. It's not like you have a short to ground or anything.
So the only way that the controller can be receptive to be getting stuff is if they have their output reg high.
Correct. Yep. And so now the controller has released the line. It's not sending any data. It's going to send over some clock edges, right? Usually, I should have. I don't have this particular device set up the best. Usually, it's only 8 clock cycles at a time, 8 or 14 or 10. It's not always sending out the clock, but now it's sending out the clock, and then the peripheral can send data back as it sees fit. It sends out 8 cycles. Here's data, and now it can be transmitted to the other side. Yeah.
If you have multiple controllers, how do you decide which one is?
So they have to fight it out. Have multiple controllers. Basically, controller A, let's say, wants to have access to the line. It looks to see if anybody has traffic on the line. It pulls it low and makes sure it's getting pulled low. And then the first time it releases it has to make sure that it can be released. If it's not being released, then it has to back off because you're assuming some other controller came in there and tried to do a task. And so each controller has to have a little bit of logic to give up the line when no data is going through. Yeah.
So when you're trying to send data and you're holding the line, you're only holding the line when you're trying to send a 0.
Correct.
Is that a problem? Or
You're letting the line high when you want it to be a 1.
Yeah.
That's great. 1s and 0s. We figured out how to send 1s and 0s. 1s, 0. It just happens to be that the mechanism for driving this line high isn't the controller, because there's no PMOS gate up here. It's this pull-up resistor over here. That's fine. Logically, it still works.
Okay, if you're trying to send a 1,
Yep.
and the other target's trying to talk to you at the same time for whatever reason.
Bad news bears. Right, but a target should only be talking when it's been told to talk. And the part I'm not, and how is it told to talk? First, the controller says, hey, address whatever, right? Address XXX, you tell me the information stored in this register. And then it will send that back on the next 8 clock cycles. So the targets don't get to choose when they talk, right? Only the masters or the controllers control when the bus is activated.
Choose which address to talk to through SDA. Where's the address line?
There's no address line. This is the line. This is the only data line.
Does the address do that?
Yeah, it sends all the data, address data, data, everything through the data line. So it's nice in the sense that, hey, I only have to have 2 wires. It's just that you have to do a lot with those 2 wires. Yeah.
So you said there's a problem if you have multiple controllers.
Yes.
With this current thing.
I mean, the controllers have to be responsible to back off when they see the bus is busy when it's not them acting on the bus. So there has to be extra logic built in.
Okay, great.
All right, so let's talk about these resistors. So these resistors here, they make nice square waves, but the reality is that there is capacitance on these things. And what did I put on here? Like this is like 500 nanofarads. That's pretty reasonable for the amount of capacitance that would be on a bus line. And so you can actually start seeing that here. We start seeing this little arcing, right? So this is the RC charge up. Now these clock look pretty good, and if I send data over, you can see, oh, come on, let go. You can see it took a little RC charge up time. That's fine. But if I start increasing my capacitor size, what is it, 700? Let's go. I don't think I made them big enough. But you can start seeing that I've started increasing the capacitor size, and now the RC charge goes longer and longer and longer. And you could imagine we could get to the case where the RC charge up time is so long, there's so much capacitance, I would miss my timing. So let's just go here, and I'll say this is 10. And now I'm trying to get a clock. This clock period is trying to be this. It didn't even get over VDD over 2. right? It's just not possible for this bus to go this fast. It cannot meet this timing requirement, but let's make it meet this timing requirement. So I'll go over to here, and I'll increase the rate, right? It can't pull up. This resistor is not large enough to pull this line all the way up, so let's increase its power, and I'll give it, let's say 500, oh no, 0.5K. Oh, it did a little bit better. These are just made up numbers right now. I'll give it 100 ohms. That would be a crazy amount, but still here it works, right? Here I'm able to get it all the way up, and I'm able to meet, I'm actually not even able to pull it down low enough because of this internal resistance, but I had made up numbers, it doesn't really matter. I'm really showing you, hey, if you have too much capacitance, decrease the size of your resistor to cause it to come up fast enough. There's this trade-off you have to do. This is why you want to go to faster data rate on your bus. Well, that's why on that previous slide we had different resistor values for different speeds. No questions? Yeah.
So the transmit data, you would probably need to start with a low, because otherwise if you just like keep it high, you can't differentiate between like it being 1 on the first bit versus it just being.
Yeah, let's look about the, so this is just on bit signaling right now. Let's go over to like the MAC layer. We'll do that next. Kind of see what that looks like. All right, so the starting sequence here is that you have a clock. The clock is normally held high. I know in that last diagram we showed the clock going all the way through all the time. Normally it's only clocking out for the bits it's trying to receive, so it's pulses just like SPI. The starting sequence is SDA is pulled low, then the clock goes high. So this is trying to tell the peripherals, hey, look, there's something's going to happen. This is the starting sequence they're looking for to make sure everything works. Then this is the most wildest clocking scenario I think I've ever seen, and that is that the bit transition is not clocked in or out on the rising or the falling edge. It's in the middle. Right? So the clock actually occurs inside the data, both edges, the rising and falling edge happen to be inside the clock. Okay? Here, 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 here. So that means, so here, for instance, SDA is sending data out, and then the clock is going inside. So when the peripheral is sending data back, it sets the data up, looks for the transition, and then waits a little period of time, clocks the data, makes the transition of the data down. So it happens on both sides. Talked about this one. So during data transition, the controller is constantly checking to see if the SDA voltage matches what it's sent. So here, SDA is either going to be high or low. It's trying to check to see, is that actually true? Because it could mean that some other peripheral or other issue happened that's trying to take control of the bus. And if that happens, it's supposed to end its communication. It cancels that packet and then restarts and waits for the controller to be available again. So here is an example of a typical transaction. So here we have SDA and SCL. So we have a controller that's going to send out data. It sends out address bits because the arbitration method is that each device, when it's manufactured, has an address burned into it. It's not unique per device. It's unique per class of device. So like all ADM, not ADM, say analog devices, particular accelerometer, say whatever, all of those, any product SKU will have a unique address, but not every device has a unique address. There's some where you can control the last bits of the address by shorting or pulling a particular pin up to ground, or up to VDD. Anyways, we have our start sequence. We're sending an address bit out. So all this does is just say, hey, that device over there, this is the one I'm talking to, but what do you want to say to it? That's typically followed by the data round. So here, address and then data, and now we're sending out 8 bits of data. Now, if you want the peripheral to talk back to you, you'd probably set it up. You send, hey, address this, get me some piece of information is contained in data, and then it will send out an address with blank data bins is sending out edges, and now it's the peripheral's job to fill in this data, which goes back to the controller. So this way, the controller is the one that's always sending out the address bits. It's not the peripheral that's deciding where to send it. It's always the controller. So this is 90% of how arbitration's taken care of, because first it's the address, but also control over the bus is defined by the controller, not by the peripheral. The other interesting thing here is in this packet that's being sent, this address packet that's being sent from the controller to the peripheral actually responds. Inside this packet, the peripheral responds, that it acknowledges this packet. So this is an ACK or acknowledge bit. Sometimes we call it NAC, meaning non-acknowledge. And what happens is you don't know if that peripheral is actually on there. So you send an address bit, and then the so this is controller, read write bit control, and then it's the peripheral acts, pulls that line down saying, yes, in fact, I've acknowledged this message. Because if it doesn't acknowledge this message, there's no reason to send the data doesn't exist. I mean, there's nowhere for the data to go. So oftentimes, what students will do is they'll look at their data and they'll say, every time I talk to my peripheral, it knacks every single time. This bit is high. Why is it not responding? It could be miswired. The same thing happens if the device isn't even on the bus. It will knack because the pull-up resistor is pulling it high. How do you feel about that? You guys give me the looks like this guy is just talking, not making any sense. He's lying about how electronics work.
So I was wondering, given that with this setup is happening within the middle pulse, does it, I guess, work regardless of the mode that we talked earlier?
Well, that's for a whole different protocol. That's for a thing called SPI. We're talking about I2C. Yeah.
Wait, so is the second part of that diagram coming from the peripheral, or is that also a controller?
So the clock lines are all coming from the controller. If it was a write bit here, then the data comes from the controller. If it's a read bit, then the controller wants to read data. It's coming back.
And that ACK when it's reading, that comes from
This ACK, yeah. So this ACK says, I have acknowledged your address. I'm here, I can do it. This ACK says, I'm done writing the data.
And the controller ACKs too.
Oh, sorry, yeah. The controller ACK says, yes, I have the data. It's the other thing that ACKs. Yeah.
Could you explain again what happens when it's not connected, the peripheral?
Oh, when the device is not connected and the students are confused, and I'm confused too, when I was a student. So if we go back to this, you guys can see that. So the challenge here is, let me undo this. Run. So let's just say this thing is gonna knack, right? Not acknowledge, no, I didn't receive this, or it's not me. Or what could knack else mean? Address not found, let's say. So you could be writing, you set up your hardware, you say, I'm writing the right address. I've looked at my logic analyzer, I'm sending out the right thing. I looked at my code, I'm 100% guaranteed I'm sending out the right address. Why is this thing not knacking? Well, this thing allowing this thing to rise high to send out a 1 is the exact same of this thing being disconnected. If I disconnect it, that line is still high. Because the thing that pulls it high is that resistor, not this. This can only pull low. Nope, I don't believe you. So ask your question again.
I'm just generally lost in how it's gonna work.
Play with this.
Okay.
Go home, play with Falstad, push the buttons up and down. It will make more sense. Did you take 215?
Yeah.
You got all the core that you need. It's just a circuit. It's just going up and down. It's great. Yeah. Why do we need an ACK? I don't know. These people at Philips forced us to have an ACK. We have to deal with them. Why do we need an ACK? What is it? Maybe the question is, what does it do for us? This tells us, the controller, right, that the peripheral is actually on the bus and is ready and available to do this next part. There's no reason for the controller to send data when there's nothing there to receive it.
So it saves time.
Saves time, ensures that when you're sending data out, there's actually a thing to receive it. It could be not on the device, it could be powered down. There could be a lot of reasons why the peripheral is not able to respond. It could be busy. You could have asked it to do a thing and it needs a certain timeout, and it's just not ready to do a task.
How do you add to the peripheral when you're reading?
I don't know why you would need one, because usually the controller is smart enough and capable enough to know that, hey, I was expecting data, I didn't get data, it can ask again. But this is just a feature of the protocol where it's saying here, I'm done, I'm not done. It's just an option. Okay. Yep. This is what normal I2C data looks like. Oscilloscope plot. Here we see the start sequence where SDA was pulled low before the clock. There's a little bit of timeout here, a little bit of time. Now you see the clock pulses. There's 8 here, there's 9, there's 9th for the ACK bit, sorry. Then there's 8 here, and then there's a little bit of, this is between the packets, so it's gone back high. It's released the bus essentially, then it does another start event. And then you can see where each one of these clock pulses is in between those data. And here, you know, obviously you can't see the transition, but it was 0, 0 here. You should be able to walk through yourself through this and decode this bus traffic and be able to come up with those ACKs and NACKs. Yep.
Why is the top stop?
Why is the top stop?
The clock. There's
Yeah,
the clock isn't going.
It only, yeah, I confused you with the false stat. Clock only sends out bits for data that's going to be clocked in. It's not sending out clock. It's not sending out a clock for bits that don't exist. Just like same with SPI. Yep.
Wait, so you don't need a serial protocol handshake thing, wherever you can just turn on the clock and send the data.
Yeah. I mean, when you say handshaking, you mean there's no chip select, right? What do you mean by handshaking?
Yeah, like you are like start with like a low bit.
Yeah. Well, there is that. We have a start condition where the SDA has to be pulled low before the clock is.
So you have to do the start condition, and it would just start when you throw the clock.
Yeah, so here's the clock, here's a start condition, so there is a start condition. There's a stop condition, right? The clock is pulled up high, and then SDA is pulled up. So there are some conditions. It's not, they're just different than an I2C. Yeah.
Okay.
Or SPI, or UR, sorry.
When the peripheral is sending data back,
yep,
the microcontroller is anticipating when it's sending back, so it's going to drive the clock then?
Correct.
Does that defeat the purpose of like the peripheral wanting to talk to the controller on its own?
The peripheral cannot talk to the controller on its own. 2 controllers could be on the bus. Rare condition. I highly encourage you don't do this, but you can. The protocol allows it. In that case, 2 controllers could try to be taking control of the bus, and there's an arbitration scheme to kind of deal with that. That's where it's trying to look at every bit it's sending out and making sure that that bit is actually being sent out. But the peripheral cannot initiate conversation. It would have to have an external wire to do an interrupt. Okay. Yeah. Okay, talked about that. Let's see. Okay, so for your I2C, on your device, you have 4 I2C modules, which seems insane to me. Again, you have a really big chip. But what it does allow is oftentimes you want to make, say you want to have 2 of some chip. You want to have some distance sensor on your device. But they both have the same I2C address. This is a challenge. It's a challenge that comes up all the time. Because they're both, say, IR distance sensor from Micron or something. Micron has only registered 1 address. So now you want to get 2 on there. Well, if you put them both on the same data clock and data line, then they're both going to try to respond. It's going to be a mess and it won't work. So what you need to do is you could have a couple different solutions. One is you could have multiple I2C modules, and then you put them on 2 different pins. You have to use more pins for this, but now you can talk to both these devices. That's kind of maybe the cleanest way if you have the pins. The other one is these device translators, where you go right to them and either through hardware, like a resistor or something, you have a translator where you send an address and then the translator will turn it into the correct address. And so from the peripheral's point of view, or for the controller's point of view, there's two different addresses, even though they go to identical devices over there. So there's these hardware tricks you have to do to get around it. Anyways, and for your projects, you do not have to worry about that, probably. Yeah, so on device you have packet error generation, and it will validate that you got NACS and ACS when you were supposed to, which is nice. I think you can send interrupts based on that as well. So the pros and cons, so easy to wire, only 2 wires plus ground, widely supported. It's very common now to almost get every flavor of peripheral that you want in either I2C or SPI. Oftentimes they're both baked into the same piece of silicon, and there's just a toggle bit, some pin on the outside you have to raise high or low. The cons is this open collector, which makes debugging challenging. Speed, there's a speed and power trade-off, which is interesting. The max speed is defined by resistors. Well, let's just say resistors and your parasitic capacitance together, not by the performance of your chip. And there's no hardware arbitration, that really helps you solve that problem in the sense that there's no chip select line. This all has to be done through the protocol. So to review, let's see. We talked about I2C. Oh man, we're not gonna have enough time. Yeah, we'll do it real quick. I'll make you. It's horrible. Nah, we'll do it. Yeah, we'll do it for next class. It's fine. Let's do the review now. So for chip, UART is chip-to-chip communication. Typically, there's only one transmitter, one receiver, one device, another device. There's not multiple devices. But there's no idea of master or controller here. Remember, they both think that they're the transmitter. They both think they're the receiver. There's no mixture here. There's not that TX doesn't go to TX. You go the other way. It's one of the oldest protocols, and there's no clock. So this is really good for, say, talking from your device to a USB peripheral. So something will translate UART to USB or UART to wireless, like XB or Bluetooth. The other parts are there's no clock, so these devices have to do clock recovery on their own. The reality means that you probably aren't going to go as fast. This is not going to be the fastest protocol in the world, but it's fairly easy to implement and only costs 2 wires. We talked about SPI. So here you have serial data out, serial data in from the perspective of the controller. The controller sending out a clock, and the controller is going to select which device to use. This is probably the most like the APB bus peripherals that we talked about in memory mapped I/O. And then I2C, ooh, that got out of order. Open collectors, and each device has a unique address, 0 for broadcast, and the speed is defined by hardware. And we will end there, and we'll have a worksheet when you guys come back on Wednesday. All right, thanks.